All right, this is Brian, and in this set of slides, we want to look at modes of heat transfer. Now, I've talked about one, and that's evaporation. When liquid turns into a vapor, it carries away energy, and that is one way that you can exhaust heat to the environment, or if you blow on cocoa, you cause it to evaporate, and that causes it to cool. We also have conduction, that is putting a hot object in contact with a cold object, and heat flows from the hot one to the cold one. There's convection, which is the motion of warm fluids, and that can carry heat. And we have here a Schlieren photograph of kind of a hot goblet, and it's carrying away, you can see it's like heating up air, and the air is carrying away heat. This is really hard to calculate, so we're not going to do much with that. But we will talk about radiation. Anything that's warm emits thermal radiation. And right now, you are emitting thermal radiation to the environment, but anything that emits thermal radiation also absorbs thermal radiation. So you are absorbing thermal radiation from the environment as well. And the amount that you are absorbing and the amount that you are emitting is staggering. And that is something we're going to talk about in this set of slides. Okay, first, just to put things in perspective, I want to ask you this question. Would you rather sit in a room with warm air and cold walls, or pull down your trousers and sit on a cold steel bench? And I know this sounds like a silly question, because it is, but there's a point to it. And the point to it is something we'll return to at the end of this set of slides. But let's start by looking at conduction. Now, when I have a hot object and a cold object, and they're separated by some sort of material, heat is conducted through the material from the hot object to the cold object, and the amount of heat that is transferred, that's Q, in a time delta T, is given by this relationship right here. It's K times A over L times delta T. Delta T is the temperature difference between the two sides. K is the coefficient of thermal conductivity. A is the area, the cross-section area. L is the length, how much distance is between the two. And it's a fairly straightforward relationship to figure out. The heat capacity of different substances really varies significantly. I want to mention a couple of things. If you look at concrete, which is very much like tile, the thermal conductivity about 0.8. Check out carpet, about 0.04. That is less by a factor of 20. So when you get up in the morning and you stand with bare feet on a carpeted floor, or you stand on a tile floor, the tile floor feels colder. In fact, they're probably the same temperature, because pretty much everything inside your house is about the same temperature. But one of them carries heat away from you at a greater rate. And so as a consequence, it's going to feel colder. When you feel cold, it just means you're losing heat at a great rate to the environment. Now let's look at a conduction problem. Oh, and it's the sitting on the bench thing. So suppose you're sitting naked on a steel bench and the temperature is 0 degrees Celsius. And the only thing insulating your body and the core of your body, which is at a temperature of 37 degrees Celsius, we will say, is a layer of skin and fat. And we'll assume that that insulation is comparable to a layer of pure fat that's 1.2 centimeters thick. And actually, that's pretty reasonable. It's less fat than that, but a little bit of skin. But just to make the problem simpler, we're going to assume a layer of 1.2 centimeter thick, half an inch thick layer of fat. And actually, you have a layer of fat approximately like that, and that's good, one, for cushioning when you fall, but also two, for insulation. And then we're going to answer this question: what is the rate of heat loss by conduction to the bench? First, we strategize, and we're going to say we're going to treat this as a problem of heat transfer by conduction. And that's fairly straightforward. And our preparation step looks like this. Now, when we have things that are being transferred from something that is hot to something that is cold through some intervening medium, okay, we have a relationship that describes the heat loss, and it's this: Q over delta T, the amount of heat that is lost in a time interval delta T, is equal to K times A over L times delta T. Okay, that's my basic relationship. And here's some of the quantities that we're going to need. K is the coefficient of thermal conductivity. And we saw on a previous slide that the coefficient of thermal conductivity of fat was 0.21 watts per meter per Kelvin. So we're going to multiply by a temperature, but we're actually going to be multiplying by a temperature difference. And the temperature difference, it doesn't matter if it's in Celsius or it's Kelvin, so everything is going to work out just fine. The area through which we lose the heat is just the area that was given in the bench. The area given in the problem statement, the area in contact with the bench is 0.16 square meters. L is the distance through which the transfer occurs. That is the 1.2 centimeter layer thickness, or 0.012 meter layer thickness. And delta T is the temperature difference between the hot and the cold. And we're told that the inside of your body, we're assuming, is at 37 degrees Celsius, and the steel bench, we're told, is at 0 degrees Celsius. And so we have everything we need for the next step of our problem-solving strategy, which is solve. And if we solve this, if we go ahead and put in all the numbers that we have, so we just go ahead and do the computation, what we get is this. We get 100 watts. That is 100 joules every second, okay? Now that's a lot. That is a lot of heat loss, and it's not a surprise. I mean, if you sit on a cold steel bench with a bare bottom, you're going to lose a lot of heat to the bench, and so it's not a huge surprise that that's true. But to put it in perspective, this is approximately equal to your basal metabolic rate. Okay, so if you do that, you're going to be losing heat about as quickly as your body is converting chemical energy to thermal energy, and so you are going to feel very, very cold. This will be uncomfortable because you have other means of heat loss, and you're going to be losing heat at a greater rate than your body is making it. You will feel chilly. Now, I want to show something really quickly, and that I redid the calculation not for a human, but for a rat. And we just assumed the rat was lying on the steel bench, and I got some values for rats, came up with some numbers, and we assumed the same difference between the body temperature and the bench temperature. There's a layer of fat on the rat that, of course, is less thick than the layer of fat on you, and the area of contact in the bench with the bench is less. If you do the calculation for a rat, you end up with a power loss of about 10 watts, less than for you because there's less area mostly, but that is 5 times the rat's basal metabolic rate. So if you're a rat and you're lying on a cold steel surface, that is rapidly going to be life-threatening. This is dangerous, not just unpleasant as it would be for you, but actually dangerous. So smaller animals are going to lose energy at a greater rate due to conduction. So as a consequence, if you're an animal that's going to be outside and you're laying on cold surfaces, you want to be big. If you're a polar bear, you have a thick layer of fat and you're large, and your surface area to volume ratio is such that the rate that you're losing energy at is actually quite fine. As a matter of fact, with polar bears, getting rid of energy is a bigger problem than staying warm under many circumstances. So if you go big, the energy loss to the cold surfaces is not going to be such a big deal. Now I want to talk about radiation. And there's a relationship in the book that looks like this. And this is the energy loss, or the rate of energy loss, Q, energy, divided by delta T. So this is basically a power. And it's equal to the emissivity of a surface times sigma, which is this constant, times the cross-section area of the surface, times the 4th power of the temperature. And notice this must be in Kelvin. You have to put temperatures in Kelvin in order to make sense of this. Okay, that is the amount of energy that you lose by radiation. Couple quick things. First off, anything that's warm emits radiation, and the warmer you are, the more radiation you emit. Seals actually have little thermal windows. They will have patches of them that they get to a really high temperature that they use to exchange heat with the environment. This temperature on the seal is as warm as your skin. This temperature is nearly freezing. And so there's a huge difference between different places on the seal. And that's actually the patches of the thermal windows on seals are as indicative of what seal you're dealing with as your fingerprints are of you. So you can actually spot which seal is which by looking at their thermal windows, which is kind of cool. Another thing I'll note is that snakes, and there's particular kinds of snakes known as pit vipers, of which rattlesnakes are an example, have these vision organs in front of their eyes that sense thermal radiation. That's basically a second set of eyes that is intended to sense this radiation right here. And you emit that radiation just because you're warm. And so if you're hiking and you see, on a cold morning, and you see a rattlesnake, the rattlesnake can see you even in complete darkness. It can sense the radiation you emit. Kind of a crazy, crazy thing. Now, there are also cameras that can do this. Okay, and here's a woman out walking her dog, and you can see warm eyes on the dog, and the dog is leaving a little something on the pavement, which is nice and toasty as well. And you can see her hands are warm, and you can see a warm spot from her neck, and you can see the thermal radiation from like hot things, and you have less radiation from the cold things. And you've seen thermal images like this. They are made basically by sensing the thermal radiation that things emit. And I want to do a quick calculation, and this is one that I have data for it that came from some studies of thermal comfort that were done back in the 1950s. And people were basically doing experiments with subjects to see, like, what did it take to make people feel comfortable? If you're in your house in the wintertime, you want to feel comfortable, and what sort of things affect that? And they changed the wall temperature and the air temperature and the humidity, all kinds of different things. And something that was a surprisingly big effect was the temperature of the walls, and we will see why. Now, you have about 1.8 square meters of skin, and if you were unclothed, your skin temperature is going to be about 33 degrees Celsius. If you're in a room with dry air of 24 degrees Celsius, this is from those papers that I looked at. So suppose we keep the room temperature at that. And then we're going to vary the temperature of the walls. First, we're going to look at how much energy you radiate away. Second, we'll see how much you absorb by radiation from the environment. And the amount you absorb depends upon the temperature of your environment. And then we're going to look at your net loss. We're going to redo the calculation and say what will be the net loss if we make the walls much, much colder. Okay, that's the calculation that we're going to do. First off, we strategize, and our strategy is to say this is a problem of thermal radiation, and so we're going to treat this using our basic relationship of the Q over delta T is equal to E times sigma times A times T to the fourth. That is how we're going to complete the calculation. In our preparation step, we're going to do this. We're going to say here's a person, okay, here's a person which has a surface area of 1.8 square meters. Okay, that's my surface area. The person's emissivity is 0.97, and that is true for skin of any color. Okay. And then my constant sigma, just to remember, is 5.67 times 10 to the negative 8. That's the value of it. Okay. And then we're going to figure out how much energy the person radiates and then how much energy the person absorbs. And in both cases, we use the same relationship. And it's Q over delta T is equal to E times sigma times A times T to the fourth. A is the surface area of the person. Sigma is that constant. E is the emissivity. T, for the emission, is the temperature of the body, 33 degrees Celsius. That's for the emission. For the absorption, it's the temperature of the environment, which is either 24 degrees Celsius or 10 degrees Celsius. Those are the two values that we'll look at. Now, we're going to need to compute using this equation right here. And this equation requires temperatures in Kelvin. So I'm going to go ahead and take my temperatures and put them in Kelvin to save me a step later. 33 degrees is equal to 306 Kelvin. 24 degrees is equal to 297 Kelvin, and 10 degrees is equal to 283 Kelvin. We need those values. And now we're ready to solve. And if we're solving for the energy a person radiates, and we're gonna compute a power, okay? It didn't ask, but it said how much energy is the person's body radiated away. Let's just say per second, and we're going to treat it as a power. So the power that you radiate away, Q over delta T, that's the energy divided by time, that's a power. The power that you radiate away, E times sigma times A times T to the fourth. We talked about all those numbers. The crucial variable here, of course, is the temperature in Kelvin, 306 Kelvin. And you end up with an amazingly large value. You end up with a radiated power of 870 watts. And that's kind of amazing because that is 8.7 times your basal metabolic rate. So you're radiating energy away at a ferocious rate. If you didn't have any way of replenishing this, you would quickly cool off and die. But fortunately you do. If the walls in the room are at 24 degrees Celsius, the amount that you absorb, we calculate exactly the same way. The power you absorb is equal to E times sigma times A times T to the fourth, exactly the same thing, except the temperature is not the temperature of your body, it's the temperature of the environment, which is 297 Kelvin. If I put that number in, I calculate the amount of energy that you absorb is 770 watts. Now that's reasonable because then you're emitting 870, but you're absorbing 770. Your net loss of energy by radiation is just 100 watts, and that's just equal to your basal metabolic rate. And if that's the only a significant form of energy loss, and in fact it is, you'll feel actually quite comfortable. You'll feel quite comfortable. But suppose we took the walls and make them colder. If I took the walls down to 50 degrees Fahrenheit, so I took them and made them 10 degrees Celsius or 283 Kelvin, what will be the net loss of energy by radiation? And if you complete that calculation, what you get is a whopping 235 watts. And that will be distinctly unpleasant. You're losing energy at more than 2 times the rate your body is generating it, and so you are going to feel cold. You will feel quite chilly. And that's in a room with exactly the same temperature air. The air is still warm, but the walls are cold. And if the walls are cold, you just don't get as much energy by radiation from the walls. And as a consequence, your net loss by radiation is quite large, and you will feel quite chilly. And that was one of the things they discovered in these studies of thermal comfort. More important than the air temperature was the temperature of your walls. Right now, I am doing this in a room with a lot of windows and I've got some French doors. I would guess that a quarter of the wall surface surrounding me is not walls, but it's glass. And the glass is a really good thermal conductor. It's very, very chilly. And even though the air temperature in this room is the same as in other rooms of the house, I feel chillier here because I'm radiating energy outward and I'm just not getting the love back. And so the temperature of the walls, very, very important. And my assessment is this is kind of crazy. These numbers seem amazing, but that, in fact, is how the world works. And when you do future calculations, you'll be able to use this as a benchmark for comparison. Now, I want to bring up a fact about penguins, which is kind of awesome. Okay, so here's an emperor penguin on the ice in Antarctica, and it's underneath the sky. And the sky doesn't radiate very much energy in the Antarctic winter. So the penguin is radiating energy upward and it's not getting the love back. And so as a consequence, the penguins radiate so much energy that the surface of their skin can actually be colder. It can actually be colder than the temperature of the air. So the surface of the body is actually chillier than the air temperature surrounding them. And they're so well insulated, they can make this work. And you have a homework problem dealing with this. That's kind of an amazing, amazing thing. But now back to this question. Would you rather sit in a room with warm air and cold walls or pull down your trousers and sit on a cold steel bench? Of course, there's some quantitative details here. There's some numbers. But it turns out sitting on the cold steel bench meant you lost energy at a rate of 100 watts. Sitting in a room with warm air and cold walls meant you lost energy at a rate of 235 watts. And so this one is actually apt to be less comfortable, which is kind of amazing. And it just speaks to the importance of radiation as a heat transfer mechanism. Important, but underappreciated, and extremely important for the fate of the planet, which is something that we'll talk about in a future set of slides. But first, we need to talk about fluids, and that is going to be our next big topic.